So today in this session we are going to cover central limit theorem. We are using Rice University's simulation demonstration website, and this is specifically sampling distribution demo from Rice University, and I'm going to demonstrate the central limit theorem using this. So first we are starting with a population of data here. So right up at the top, if we collect the data, draw a histogram. The data, it spans from 0 to 32, the data. And then the summary statistics, let's focus on two summary statistics. The mean is 16, standard deviation is 5. And I'm going to take a sample of size 16, n equals 16, that's my sample size. I'm going to take samples from here. So second row, I will show the sample data. And then the third row, I'm going to compute the mean from these 16 samples. And then I'm going to draw the distribution of the sample means in the third row. And we are going to ignore the fourth row at this point. So with the sample size 16, let's take one sample of size 16, okay? So I'm animating one sample. So you see 16 samples I'm collecting. And so these are the 16 data points that are collected from the parent population. So you see 16. And then the third row here, I'm computing the mean of those 16 data points. So I have one mean value now. That is 16.31 that you see here. And then let's focus on mean, that is 16.31 on this one sample. Mean of this one sample. And then the standard deviation is the standard deviation between different sample means. So I have only one sample mean at this point. So my standard deviation is 0. Okay. So let's take another sample. So I'm collecting a second sample of size 16. So I'm computing the mean of those 16 samples. And then so I've got two sample means here. So the mean of the two means is 15.46 here on the third row. And then the standard deviation of these two means, that equals 0.85. Okay. So let's say I repeat my sampling process. Let's say I'm repeating this 1,000 times. So now I have collected 1,000 samples, actually 1,002 samples. And from each sample, I've calculated the sample mean. Then I'm drawing the histogram of the sample means. Now you can see that the original data span between 0 and 32, but the distribution of my sample means are very, very tight. You can see that. So intuitively, you can see that the raw data spans 0 to 32, but then I'm taking a sample of size 16 and computing the mean. So the low and high are kind of averaging out. So my sample mean is going to be very, very close to the original mean. So now the original mean up at the top is 16. So the mean of all the 1,000 means is 16 on the third row here. Mean of all the means, sample means. Then look at the standard deviation of the sample means. That's 1.26. You expect the sample means are going to be very, very tight to each other. So you would expect the variation of the standard deviation of these sample means to be very small. So it's 1.26 compared to 5. So if you notice the relationship between the two means are exactly the mean at the top, which is mean of the original data values, versus mean of all the sample means, the two are exactly the same. But if you look at the standard deviation of the original data points was 5, but the standard deviation of the sample means is very, very small, 1.26. It's precisely 1/4 of it. Okay. So you can see the sample size is 16. So if you take the square root of 16, that's 4. So you can kind of see that this standard deviation of the sample means is 1/4 of the original standard deviation. Okay. So now let me change the original distribution. Let's say that's uniform. So that means that any data value between 0 and 32 is equally likely. So it's equally distributed. So now I'm going to take one sample of size 16 from this population. So I'm taking one sample right now, and all the data values are equally likely. So now I'm computing the mean of those 16. That comes out to be 17.9. Okay, let me take another sample. Let me animate. The second time I'm taking a sample of size 16. I'm computing the mean of those. That is this value here. So now let me repeat this process 1,000 times. So now based upon 1,002 samples, each a sample of size 16, I've computed the mean, sample mean for each one of those 1,002 samples, and this is the distribution of sample means. Again, you can see that the distribution of the sample means is bell-shaped or normally distributed. And let's look at the mean. The original mean of the original distribution 16. The mean of all these means is very close to 16. And the standard deviation of the original population is close to 10, and this is 2.5. Again, you see the relationship, it's 1/4. This standard deviation of the distribution of sample means is 1/4 of the original standard deviation. So let's take a skewed distribution, and let's repeat the same process. Let me animate. I'm taking one sample of size 16 from the skewed distribution. I'm computing mean of that sample, so that's 7.6. So let me take another sample. So I'm taking another sample of size 16, compute the mean. I'm plotting it here, and I'm repeating the process. Let me repeat that 1,000 times. And then now again, I've got a bell-shaped curve for the distribution of the sample means. The original mean was 8.08 for the original distribution, but the mean of all the sample means, that's 8.12, so very, very close. So the mean of all the means is very close to the mean of the original population. Again, the standard deviation 6.22, now it's 1.6, again it's 1/4. So you see the same pattern. The mean of the original population, mean of all the sample means is exactly the same, but the standard deviation is 1/4 of the original standard deviation. So now let me go back to the normal distribution. Now I'm going to change the normal distribution, so it's not skewed, it's not uniform, it's not normal, it's some random distribution. So here there is no pattern here. So it is some random, kind of distribution. So the mean is for this is 16, standard deviation 6.35. So if I repeat the process here, so I'm taking one sample of size 16 from this random distribution, computing the mean, and then let me take another sample from the random distribution. I'm computing the mean. I'm repeating the process 1,000 times. So now you can again see the distribution of the sample means. Again, it's normally distributed. If you compare the mean of the original distribution, mean of this, all the means, 1,000 means, it's exactly the same, 16 versus 16. Standard deviation of the original population 6.35, it's 1.61. It's 1/4. So what we are demonstrating here, no matter what the original distribution shape is, whether it's a normal, uniform, skewed, or any random shape, if you start taking samples of size 16 from the original distribution, then the distribution of all the sample means is always going to be normal, and the mean of this the sampling distribution of all the means is going to be exactly same as the original mean of the original distribution. The standard deviation of this bell-shaped curve is always going to be the 1/4 of the original standard deviation. So what we are intuitively demonstrate is that if you keep repeating the sampling process, the distribution of the sample mean is always going to be normal. The mean of that sampling distribution is always going to be mean of the original distribution. And the standard deviation is always, of the sampling distribution, is always going to be the original standard deviation divided by square root of n. So this is the central limit theorem. It's a very, very important theorem, and this is used in making inferences for statistics. So if you want to know how the center limit theorem is used in inferences, you need to watch the demonstration on confidence intervals. Thank you.